Hi everybody, welcome to another video in linear algebra, section 2.2, the inverse of a matrix. The inverse of a matrix, an n by n matrix, meaning a square matrix, same number of rows as columns. An n by n matrix is said to be invertible. So, invertible. If there is an n by n matrix, the same dimension, C, such that C times A is equal to the identity matrix, and A times C is the identity matrix. Of course, I is the identity matrix of order n by n. So C, A, and I all of them have the same dimension. In that case, C is called the inverse of A, and denote A to the -1, or we just say A inverse. So we have A times A inverse is equal to I, and A inverse times A is equal to I. A matrix that is not invertible is called a singular matrix, and an invertible matrix is sometimes called the non-singular matrix. So singular does not have inverse. Singular matrix does not have inverse. And invertible matrix is the matrix that has an inverse. And an inverse matrix, if there exists, is unique. Right. So let A be that matrix and C be that matrix. Determine whether C is the inverse of A. So all we need to do is just stick to a definition. We're going to check both of these conditions. First, C times A is that equal to I. So C times A, C, -7, -5, 3, and 2, times A, 2, 5, -3, -7. So -7 times 2, -14, plus 15, that is 1. -7 times 5, -35, plus 35. 3 times 2 is 6, minus 6. 3 times 5, 15, minus 14. And this is the identity matrix. We have 1 on the diagonal and 0 everywhere else. So yes, this condition check. Still need to check the other direction. That is A times C is A times C equal to I. A 2 times 2, 5, -3, -7, times C right. 2 times -7, -14, plus 15, -14, plus 15 is 1. 2 times -5 is -10, plus 10. -3 times -7, 21, minus 21, and 15 minus 14. So yes, it is also check, because both of them check. Both of these conditions are satisfied, so we say A is equal to C inverse, or we can say C is equal to A inverse. Of course, if we enter the matrix, (2, 5, -3, -7, inverse, and we do have the matrix C. Right, so that's good. Right, so certainly we can check to see if the matrices are inverse of each other. Now, for 2 by 2, only for 2 by 2 we have the formula to find the inverse. Let A be the matrix of A, B, C, D with AD minus BC, so the product of the diagonal and difference not equal to 0. In that case, the inverse is given by this. So what we have is the matrix A, B, C, D, A times D minus B times C. So the difference of the products of the diagonal have to be different than 0. If it is the case, what we do here is D and A. So these two matrices, we're going to swap places. So I'm just saying interchange these two entry, and B and C compared to the original, which is negate. So these two entry on the diagonal swap places, the other two change the size. Of course, and then we have 1 over AD minus BC. And make sure that we cannot divide by 0. So if the denominator here is not equal to 0, then it is invertible. So if this condition is satisfied, it is invertible. The inverse exists. If it is equal to 0, it is going to be a singular matrix or not invertible. It has no inverse. Very straightforward, right? Now, find the inverse of this matrix. So what we do is first use the form 1 over 3 times 6 minus 4 times 5. And then these two entries will be swap places, and the other two change the sign. So 3 times 6 is 18 minus 20 minus 2, 6, negative 4, negative 5, and 3. And multiply that inside, we have negative 3, 2, 5 half, and negative 3 half. Right, just check. Of course, we can change fraction. Negative 3, 2, 5 half, and negative 3 half. Yeah, the inverse should be able to, we should write that in fraction. Except in some condition that we divide by too big of a number, that would be a problem. Right. Now, look at this. Let's say B is that transfer B. Oh, sorry, the notation. Don't forget, this is where we find the inverse, right? Right, next, phi B inverse. 1 over 6 times negative 6 minus 4 times negative 9. And then swap places of these two and change the sign of the other two. Right. Of course, we can do that. However, the problem here is 6 times negative 6 is negative 36 plus 36. This is equal to 0. So, of course, we cannot divide by 0. So, when we do that, it is undefined. Right. Of course, we can check also. And you can see this is singular matrix. Of course, singular matrix has no inverse. So always say the inverse does not exist. Right. So certainly we can find the inverse of a 2 by 2 matrix very easily. The problem is when what do we do when we have higher dimension? But we'll talk about that in a minute. Now we study about matrix operation. I think I make a typo in the subtitle here. It's not matrix operation. is matrix equation. So matrix operation for matrix equation. Right. If A is an invertible n by n matrix, then for each b in Rn, the equation AXB has the unique solution x equal to A inverse B. So this is the equation and this is the solution. Right, so why do we have that? Well, one thing, let's say if we have numbers, right? Let's say we have Ax is equal to B. To solve for x, well, that's easy. Divide by A on both sides. The problem with this is in the matrix, there's no division. There's only multiplication. And there's no cancellation law. We cannot say AB is equal to AC. We cannot just cancel on both sides like this. In matrices, we cannot do that. Of course, in numbers, of course, if A, we cannot just cancel A like this. Of course, if A equal to 0, it doesn't work. Because simply we cannot divide by A. Right, so what can we do instead? Now let me write the equation AX equal to B. Right, what we can do is we can multiply both sides by the same thing. We cannot cancel, but we certainly can multiply. So multiplying both sides are perfectly okay. So what I do is multiply by the inverse. By definition, the inverse times the matrix itself gives us the identity. And by property of the identity matrix times any vector is going to be the vector itself. That's why we call it the identity matrix. So we can just say x equal to A inverse times B. Simple enough. Before we go to this example, just go over some properties of inverse. If A is an invertible matrix, then A inverse is also invertible, and inverse of inverse get us back to the matrix. If A and B are invertible matrices, then so is A times B, and the inverse of A times B is the product of the inverses of A and B in the reverse order. So the inverse of the product is the product of the inverse in the reverse order. That sounds familiar, right? Remember, the transpose of the product is the product of the transpose but in the reverse order. Same thing for the inverse. The inverse of the product is the product of the inverses but in the reverse order. Of course, the difference between this one and the inverse matrix is that all of the matrix A and B here have to be a square matrix. Remember, n by n. Same number of rows as column. Yeah, invertible matrices, always said invertible matrices, identity matrix, all of that have to be a square, square matrices only. Right, if A is invertible matrix, then so is A transpose, and A transpose is the transpose of A, and the inverse of A transpose is the transpose of A inverse. So yeah, these properties. Right, now use the inverse matrix to solve this equation. Right, so first I will write this as the matrix equation. This is easy. We did that in chapter 1. Put all the numbers, all the coefficients together into one matrix. And we put the variable into a column vector. That will be equal to the vector on the other side. Right, so here we can say this is the matrix A, this is the vector X, and this is the matrix B, or the vector B. Yep, I'm sorry, for no reason I write this as a matrix B. That should be a vector B. Sorry. Yeah, that's what it should be. Right. So the solution is going to be x equal to A inverse times vector B. So x equal to A inverse 1 over this 3 times 6 minus 4 times 5 and the inverse 3 and 6 swap places, 4 and 5 change signs, and then times the matrix B 3 and 7, right? 3 times 6 18 minus 20. I think we did this before. 6 negative 4 negative 5 and 3. Now what do we do first? Do we multiply this number to all of them and then take that multiply to this? In which case, how many operations do we need? Right, that number is multiplied to all 4 of them, so 4 multiplication. After that multiplication, we have a row times column, right? Now, if we do this first, when we do this, we only have one vector, and then we only have 2 calculations. That number multiplied to it. So multiply the second 2 matrices with some calculation, because regardless we're going to have, let's just say again, we have a number which is 1 by 1, if you will, just a number, and then we have 4 2 by 2 and then 2 by 1, right? So regardless, we're going to have to multiply a matrix to a vector regardless. But if we multiply negative 1/2 into this, there's 4 multiplication and then a matrix times a vector. Not only that, multiply negative 1/2 will give a fraction into it. Now if we multiply these two first, then we don't have to deal with fraction, which is might be better. And besides, when we multiply that, we only have one number multiplied to 2 numbers, so it will be better multiply these two first. Right, 6 times 3 18, row times column, so 18 minus 28, so that is minus 10, minus 15 plus 21 6. Multiply that inside, we have 5 and negative 3. Right, you see, when we hold that number, multiply the matrices first, we don't have to deal with the fraction, and at the end we take that number only multiply to 2 entries, as suppose we originally multiplied to it. That is a 4 multiplication here. So, and besides, if we just want a solution, of course we can, there's a lot of way to do this. We can just say it, sorry, alpha zoom, we have 3 4 5 and 6 inverse times 2 rows 1 column, 3 and 7. Of course we have the solution, of course, but the fastest way to find the solution, of course, what we learned in chapter 1, put this in the matrix matrix and reduce row echelon form. That will be the best, the most efficient way to get to the solution. Of course, what do we do? reduced row echelon form of that matrix. Yeah, you see, this is the most efficient way. Of course, the calculator they calculate this almost instantly. But let's say if we have the matrix of 100 by 100, a little bit of calculation like this will save us a lot of time. Right, but of course, you see, why don't we have a lot more example than this? Well, first of all, because that's not very efficient way to do it. The reduced row echelon form is the best way to do it. Besides, this method of finding inverse only works for 2 by 2. And you said, what do we do when we have 3 by 3 or 4 by 4? Right? Well, this is where we get into that. Right, before we go to that, we study about elementary matrices. So elementary matrices associate to elementary row operation. Remember, there are 3 row operations. Swapping the rows, multiply the whole row by one number, and then multiply the whole row by the number, add and replace to another row. So 3 row. I'm going to write that in a minute. Right, but first some definition, some note here. The product of n by n invertible matrices is invertible, and the inverse is the product of the inverse in reverse order. Oh, we already have that. Okay. Next, invertible matrix A is row equivalent to identity matrix. Alright, so now that is important. That means if we have any invertible matrix A, it is equivalent to the identity matrix. So that means if A is invertible, then we take reduced row echelon form of A is equal to I, the identity matrix. By the way, if you look, if you study in the textbook or somewhere else, this is the symbol for equivalent. So when we say row equivalent, the symbol can be said it is equivalent to the identity matrix, meaning that there will be some sequence of row operation that turn A into I. But in here specifically, we just have reduced row echelon form of A is going to be the identity matrix. Right, now on to elementary matrix. Elementary matrix is one that is obtained by performing a single elementary row operation on the identity matrix. So we have elementary row operation. So there are 3 of them. First, we can swap row I and row J. Second, we can multiply a number into a row and replace into that row. And number 3 is multiply a number into a row, add and replace into another row. So those are the 3 elementary row operation, and there will be 3 elementary matrices associated to this, which we'll study in a minute. Right, so instead of doing this, we just multiply by a matrix. If an elementary row operation is performed, the result can be written as EA. So instead of writing this, we can just multiply by the elementary matrix. Each elementary matrix is invertible. So all of the elementary matrix is invertible, and the inverse of them is the same type, but if we go back from E to I. Right, so again, those are the 3 elementary row operations, and there will be 3 elementary matrices of those 3 kinds. Right here, let's look at the example. Let E1 be those matrices. Compute E1 times A, where A is this. Now, this should be simple because those matrices are elementary. E times A, E1 times A. E1 is 1, 0, 0, 0, 1, 0, -4, 0, and 1. when we apply an elementary to matrix, it's always multiplied in front of the matrix itself. So we put that in front of the matrix A, B, C, D, E, F, G, H, and I. Right. Row times column, row times column, row times column. Yep. That's just A. Second column, just B. Third column, well, let's see, easy. Second row, first column, 0, D, and 0. Second column, E. Third column, 0, F, I, R times 0, so HS will be F. Now, we have to pay attention now. Row times column. So this is minus 4A. I should know this before I write, so sorry. Just leave a lot more space between the entry. Right, again, the first two rows will stay the same. Right, now negative 4A plus G, negative 4B plus H, and negative 4C plus I. So what we do here, what is the role of this matrix, is that it is the same as multiply row 1 by negative 4 and then add it, and then add and replace to row 3. So this is similar to, so we say for row A, what we do is do this, negative 4 times row 1 plus row 3 store to row 3. So when we do that operation, we have equivalent to the matrix E1 times A. So instead of multiply by E1, we can perform that operation. Right. E2 and A. E2 and A. Right. Row times column. So only the middle numbers have value. So row times column. So we have D, row times column, E, and F. Row times column, only the first one. So A, B, and C. And the last one will be G, H, and I. So what we see here is we're just swapping these two rows, right? As the result. So we will say the matrix A sorry, I don't know if we use that symbol or the reverse order. That's my like I said, usually I just draw an arrow. Right, so what we do here is we swap row 1 and row 2. In effect, that is just exactly the same as when we multiply E2 into A. Yeah, so that symbol is not very good because we don't know which direction. So I prefer just draw an arrow. So we know we go from here to there. Of course, if we swap rows, we go back to that. Swapping rows, different deal. Right. Now the last one, 1, 1, 5 on the diagonal. Times the matrix A. Right. What do we have here? A row times column, that's 8, row times columns B, row times columns C. So A, B, C stay the same. Next, row times column, the middle, D, E, and F, that's fine. Now 0, 0, 5 times this, 0, 0, 5G, 5H, and 5I. So what we do is we multiply the whole row here by 5. So we can say the matrix A actually just draw an arrow instead. When we multiply the matrix E3 into A, it is the same thing as multiply 5 into row 3 down to row 3. So you see each elementary matrix here will act as an elementary row operation. Now describe this we already have. So E1, that E1 is negative 4 times row 1 plus row 3 into row 3. E2, swapping row 1 and 2. And row 3, I mean E3 is 5 times row 3 replace into row 3. So those are the equivalent row operation. Now let's find the inverse. Well, this is a little more interesting. So in that case, how do we find the inverse? Right. Now, let's do the easiest one first. If we swap row 1 and row 2, the inverse of that is just swap row 2 and row 1. So pretty much row 1 and row 2 interchange. In that case, this is the easiest one. So we say E2 is equal to E2 inverse. So swapping row 1 and swapping row 1 and 2 and swapping row 2 and 1, those will be the same. So the inverse of that, we do the opposite things, which is also the same thing. But that's the easiest one. Now, next is we multiply 5 to R3 and start to R3. So in that case, what we want, the inverse. Sorry. We multiply 5 into the whole row. If we want to get back to the original GHI, we just divide everything by 5. So instead of multiply by 5, the inverse will require the 1/5, the reciprocal of what we have. So in that case, E3 inverse can be written as instead of 5 here, we're going to use 1/5. So remember, the 5 here will multiply to row 3, and 1/5 here will multiply to row 3. Of course, if we want to check, it's very easy. Yeah. So when we write the number on the diagonal, so if we want to multiply to row 3, we're going to write in here. If we want to multiply to row 1, write that in here. So it is going to be the identity matrix. We could just multiply that number into the diagonal entry. So this is the inverse, just multiply by 1/5 here. Now, the last one is a bit more complicated. How do we do the inverse of this? So inverse of this is just, we're going to just add this on both sides. And then we have the reverse. So instead of multiply -4, so we're going to do the opposite to that. So we say we're going to have -4 R1 added to the positive R3 stored to R3. So in that case, the inverse of E1 is going to be if we want to multiply by -4, we use -4. If we want to multiply by 4, we're just going to use 4. As you see, we can check. Sorry. Yeah, 1 should be there. Course, that's what we have. So whatever number we multiply by, let's say what if you want to write -5 multiply to row 2, add to row 3, replace to row 3, then how do we do it? First we're going to have the identity matrix. Just write the identity matrix. Now, what we do is we multiply by -5. So we're going to put -5. We're going to put -5. So we add and replace to row 3. So it's going to be either one of this. However, everything's spin up row 2. So in that case, the pivot is going to be that. So we're going to write right below the pivot. As here, it's based on row 1, so the pivot is on the pivot on the first row, so we write that below the pivot. So this also right below the pivot, right? So that's what we have in this case. Next, how do we find the inverse of the matrix that has more than 2 by 2? Of course, how about 3 by 3? Let's just look at the easy one first. Now, what we see here is that when we apply the RREF to the matrix A, it is equivalent to what? Multiply a bunch of elementary matrices. Let's say there's we do that m times. I don't want to mess with the n is the dimension of the matrix. I don't want to deal with that. Just use different numbers. So we use this sequence of elementary matrices multiply to A. And what did we have? The properties. The invertible matrix is row equivalent to the identity matrix. In particular, reduced row echelon form of A is equal to the identity matrix. So when we do the reduced row echelon form of matrix A, we're going to have identity matrix. Right? What do we have here? Now, compare this to A inverse times A equal to I. So this must be the A inverse, right? Because the inverse is unique. Inverse times the matrix is equal to identity. So if we find a sequence of these elementary matrices, multiply all of that together, we have the inverse. but that sounds a lot of work, especially we multiply a bunch of matrices together. So instead of what we do that, how about we do this instead? Now if we apply all of this, times the identity, right? What do we get? It's still the identity matrix, right? I'm sorry, it's still A inverse. Right? Of course, that's the properties of identity. Now instead of use identity, use all of the sequence. Instead of the A inverse, we use that long sequence of matrices times identity is equal to A inverse, right? So instead of write A inverse, we use the long sequence of elementary matrices. But then again, look at this. If we take that sequence of matrices times the matrix, that is exactly equal to the reduced row echelon form of matrix A. Now just replace A here and A here by A inverse. Pretty much what we have on the left hand side here is equal to RREF of the identity matrix is equal to A inverse, right? Of course that doesn't make any sense because I is already reduced row echelon form. So we're not going to write that equal to. But in fact, what we're going to do is this. We do the reduced row echelon form of this matrix, kind of augmented matrix, but we put that together. And when we do that, the first part of it we turn to identity, and the second part we turn to, when we apply this to I, that will be inverse. Right. So pretty much put the matrix and the identity and then do the reduced row echelon form, we will have the inverse. Right, let's try if it works. By the way, I want to use the calculator that I showed, the online calculator that will do the RIF that I showed you on chapter 1. Let me show that real quick. Right, so this is the website. Right, now if I want to find the inverse of that matrix, what I do is I'm going to put 3, -9, 2, and 6, and then I'm going to put next to it the identity matrix. And then I do the reduced row echelon form. If it works, the left hand side is the identity, the right hand side is the inverse, right? So I'm going to use those numbers. 3 space -9 space 1 space 0 enter 2 6 0 1 and calculate. Right, that's what we have. 1 0 0 and 1. 1/6, 1/4, -1/18, and 1/12. Since we do have the identities on the first matrix, so that check. So this will be the inverse. If A is equal to that, then that will be the inverse. Sorry. Yeah. So if we do the reduced row echelon form, we have the identity matrix. That check. What we have left is the inverse. In fact, if we just find the inverse of a 2 by 2 matrix, of course there's a way to do the inverse of 2 by 2 matrix, which we already did at the beginning of the section. Okay, I need inverse of that, do I? Right, change the fraction. Yeah, so that is the inverse, of course. So if you don't have the calculator and you use the online calculator, then we just have to enter the geometric matrix. But we have the matrix itself on the left, the right hand side is the identity matrix, and we just do the row echelon form, and that's what we have. And the same thing here. If we just put the matrix itself, and then we have the identity matrix, and then we do reduce row echelon form. Alright, let's use the calculator this time. Alright, so write the matrix itself and the identity matrix, and then do reduce row echelon form. So reduce row echelon form. This is 2 rows but 4 columns. Right, 4, -9, 1, 0, 0, 0, oops, 5, 1, and convert this to fraction. Once again, we do have the identity matrix here, so this is going to be the inverse of that matrix. Of course, we can always check by just finding the inverse directly. Once again, we need the inverse. Right, 1/4, now 20, 0, 1/5, yeah. Right, okay, let's look at something that doesn't have the inverse. We did have this one that is undefined on page 52, the first page of this section. Now if I'm going to put this into the reduced row echelon form, 2 rows, 4 columns. Right, so the left hand side is going to be that matrix, 6, 4, -9, -6. Right, so left side is that matrix, and the right hand side I put the identity matrix and reduce to echelon form. Let's convert to fraction. Just hit math and then go to fraction and enter. Right, now look on the left hand side here. We do not have the identity matrix on the left side. So if we do not have the identity matrix on the left hand side, the inverse does not exist. So in this case, the left hand side here is not an identity matrix, so the inverse does not exist. Right, now I just want to do this by hand, at least for one of them. In fact, let's do for one of them. Find the inverse of this matrix. So now to draw down the elimination, but this time I have to make the big matrix. And then on the right hand side, I'm going to put the identity matrix. This problem could be long, so let's fold the page in half to save space. Right, so first I'm going to swap row 1 in here, so I need the pivot to be 1. So just swap row 1 and row 2. So row 2 become row 1. One zero three 0 1 0, and then row 1 become row 2. Row 3 will be unchanged. Right, next I have the pivot here. By the way, if we have 0, there's no way we turn the 0 to 1. We cannot multiply that and turn that to 1. 0 times anything is still 0, so that's why we have to swap rows. That will be best. Now we have the pivot, we have 0. Now this needs to be 0. To eliminate this 4, we have to multiply the opposite to that, to the pivot row, add and replace to the row that we try to eliminate. Right, row 1 and 2 will stay the same. One and 2 will stay the same. Right, negative 4 times 1, 4, and negative 4 plus 4 is 0. Negative 4 times 0, 0 minus 3. Negative 4 times negative 4 times negative 3. Just negative 4 times negative 3. Negative 4 times 3 is negative 12. Negative 12 plus 8. Negative 12 plus 8. Negative 4 times 0 plus 0. Negative 4 times 1, negative 4 plus 0. Negative 4 times 0, 0 plus 1. Right. Right. 1, 0 is good, 0 is good. Now we go to second column. We have 1 already. That 0 is good. Now just need this negative 3 to 0. To do that, we use the opposite. Now the pivot is on the second row. We're going to add and replace to row 3. Right, so in that case, row 1 and row 2 will stay the same. Right, now 3 times row 2 added to row 3. 3 times 1 is 3 minus 3. 3 times 2 is 6 minus 4. 3 times 1 is 3 plus 0. 3 times 0 is 0 minus 4. 3 times 0. Alright, so we go from there and let's check. 1 0 0 good, 1 good, 0 0. Now this need to be 1, so we have 2 there, so just cut everything in half and that will be good. So we have 1/2 row 3 stone to row 3. We're going to copy row 1 and 2. And then multiply everything here by 1/2. So here we do have 1 here, which is good. 3/2, -4 times 2, 1/2, and -2, and 1/2. Right, let's check. 1 0 0 is good. 1 0 0 good. We have 1. Now we're going to turn this to 0, this to 0. I'm going to do both of them at the same time. The pivot is at row 3. So we multiply. To eliminate 2, we use opposite to that. Add to row 2, replace to row 2. And this we use opposite to that. Add to row 1, replace to row 1. Because we're trying to eliminate 3 in row 1 and 2 in row 2. Right. Do that. Row 3 will be unchanged because only 1 and 2 change. Right. I need to be a little careful here. Excuse me. Right. -2 times row 3. -2 times row 3. So -2 times row 3. Just multiply. -2. I'm sorry. 0 0. -2. -3. Positive 4. And -1. Right. Just multiply -2 in here. 0 0. -2. -3. -2 times -2 times -2, and then add to row 2. -2 for -1, right? 0 1 0, -2 for -1. Right. Next, we multiply -3 into that. So multiply -3 to the whole row here. 0 0, -3, right? -3, so -9 over 2. -3, that gives 6. And -3 times 1/2, -3/2. Right. So that's -3 times row 3. Times -3 times -3 times -3 times -3. And add it to row 1. So that will be 1 0 0, -9/2, 7, -3/2. That will be the new row 1. All I do here, just enter the matrix and find the inverse, and hopefully I got it right. Sorry. I just enter the matrix and hit inverse, so I don't even need the reduced to echelon form. keep forgetting the inverse. Right. Let's convert it to fraction. Math. Fraction. Right. Negative 9/2, 7, negative 3/2, negative 2, 4, negative 1, 3/2, negative 2, 1/2. Okay, so even though I enter a lot of, I make some mistake entering, but it always get the answer immediately, as opposed to I do all of that by hand. Right. So of course that's how we find the inverse of 3 by 3 matrix. You said that seems like a lot of work, and I agree. Is there a better way? No. So in the next section there's another way to find the inverse, but that's going to take even more time than what we do here. And then you said, how about we use the inverse to solve the matrix, the system of equation, right? For example, we did use the matrix equation to solve for it, right? I said, yeah, certainly that works. But in order to find the inverse, of course there's a formula, but in order to find the inverse, we have to use the row operation. So let's say if we want to find the inverse of that, we have to put the matrix. Of course, now 2 by 2 is easy, but I'm just going to demonstrate. So we have to do the reduced row echelon form of this. So we have the inverse. We do have the inverse. Actually, we don't. So we have the inverse here. And then we'll take the inverse, multiply to this. And you said, why do we have to go all of those trouble? All we need to do is just say the matrix, and we just put the last column here, and we do the reduced row echelon form, and that's going to give us the solution. Actually in this case will be 5, negative 3. Actually I did try that earlier, right? So we have to do a lot more work just to find the inverse, and then when we take the inverse we multiply to the last the vector on the other side. Why don't we just put the vector on the other side and just do reduced row echelon form? That get the directional solution directly. We don't have to go through all of those, perform on the identity matrix to get the inverse first, and then take the inverse, multiply to that, give us the solution. That takes a lot more work than just use the reduced row echelon form directly into the last column. So we don't even need the inverse, just go straight to the solution. Even better, when we do this, we have the no solution and infinitely many solutions. In that case, the inverse will not exist. Right. So, like I said, this is the way to find the inverse. But practically, usually, if we can have the calculator, we just put in the calculator, reduce row echelon form, and get the inverse. If we want a system of equation, solution to system of equation, don't even need to do that. Just put the last column and reduce row echelon form, we'll get the answer, because use row operation like this. And like I said, if you make any mistake along the way, the answer will not be correct. Right, so you get the point. If we want to find the inverse, of course, the calculator over there will just find the inverse. But if you don't have that calculator, we still have to enter that, the matrix and the inverse. And then put the identity matrix on the other side. And use reduced row echelon form. Okay. I'm just going to use a calculator. Actually, this time let's use the online calculator. Right. So 1, negative 2. space, -2, -1, 1, 0, 0, enter, -1, 5, 6, 0, 1, 0, enter, 5, a space, -4, space, 5, space, 0, space, 0, 1, enter. Actually, don't need that enter, and just calculate. Right, this is what we have, and when we do that, we have 1, 0, and not to mention when we do this, and if we have the bond fraction, that even more complicated. Sorry, I just copied the answer. Right, yes, put that calculator away. So the matrix, identity matrix, reduced to echelon form, we have this. However, this is not the identity matrix on the left hand side, so in that case this is not the inverse. So if we don't have the identity on the left hand side, we say inverse does not exist. So in this case, B inverse does not exist, it's undefined. Or just say does not exist makes more sense. Does not exist because we do not have the identity matrix on the left hand side. So if you use the online calculator to find inverse, just enter the matrix identity and then do the reduced row echelon form. If the identity is on the left hand side, the right hand side will be the inverse. Now let's check if I just enter the matrix and find the inverse. Right, let's use the inverse this time. Yeah, once again the inverse does not exist. Right, so that's what we have for this section. So this section we learn about the inverse of the matrix. For 2 by 2 there's a formula, because when that not equal to 0, if it is equal to 0, that not inverse does not exist. Right, if we have a matrix equation, with the solution can be given in that form, but only if the matrix itself is a square matrix. If A is not a square matrix, we cannot do this. Only for the square matrix, because only square matrix has inverse. And then in order to find the inverse of a 3 by 3 or higher, we introduce the notion of elementary matrices. And we use that just to prove the way we find the inverse is the matrix on the left hand side, identity on the right hand side, reduced row echelon form. We're going to have the identity on the left. If we have the identity on the left hand side, the right hand side will be the inverse. And if we do not have the identity on the left hand side, the inverse does not exist. Right, so that's all we have for section 2.2. Thank you for watching. See you in another video in linear algebra.